You're welcome again to Seremba Online School. As usual, my name is Katerega Fred. We are going to continue with our current electricity, and this is lesson 3. We are going to talk about Ohm's law. As you see what I've listed, that's what we are going to talk about. So Ohm's law, they can tell you, state Ohm's what? Ohm's law. How does Ohm's law state? Okay? It states that the current passing through a conductor is directly proportional to the potential difference, is directly proportional to the potential difference across its ends, or you can say between its ends, provided temperature and other physical conditions are kept constant or remain constant. So that's the statement of the law. You can take note of it, okay? It seems lengthy, but it's very simple. The current passing through a conductor is directly proportional to the potential difference across its ends, provided temperature and other physical conditions are kept constant. What is important here? Directly proportional. So current passing through is directly proportional to the potential difference, the voltage. So voltage is directly proportional. The potential difference they're talking about, our voltage in this case, is directly proportional to the current. Are you seeing it? Now when we remove the sign of proportionality, that means we introduce a constant of proportionality. In this case, our constant of proportionality we are going to introduce, I'm not going to call it K, but we are going to call it capital R, which is our resistance, Ri. So V is equal to I, R. So this is the Ohm's law equation. So that's what we call Ohm's law mathematically. Voltage is equal to I, R in this case. Therefore, we are going to see some of the applications of that law mathematically. I can give you an example that the current passing through a 2 ohm resistor, the current passing through a 2 ohm resistor is 4 amperes. The current passing through a 2 ohm resistor is 4 amperes. Find the PD, find the potential difference between its ends. I've told you when you use Ohm's law, you just say that V, the voltage, potential difference is equal to IR. Current is 4 amperes times what is the resistance? 2. Therefore, the PDV will become 80 volts. That is very simple. Are we together? Meaning that they can even add you another example, and they say that the PD, this is example 2, that the PD, the potential difference or the voltage, the PD through a 5 ohm resistor, the PD, in fact the PD across, let us call it across, the PD across a 5 ohm resistor is 10 volts. Is 10 what? Volts. Then they ask you a question that find the current flowing. Find the current flowing through that what? Resistor. What do you do in that case? You come here, you say solution. Remember our Ohm's law, V is equal to current times resistance. But according to that, we are having the voltage which is 10. This is our PD. Across 5 ohm resistance, 10 volts. That's the voltage. Then our current, the one we are looking for, times what is the resistance? 5 ohms. The resistance is 5 ohms. Therefore, here we are having 10 is equal to 5. I divide by 5, divide by 5. This means that our current is the same as 10 out of 5. That is 2 amperes. That's the current which will flow through that 5 ohm resistor. So in other words, V is equal to IR. That means current can be the voltage out of resistance, and resistance can be voltage out of the current. In that case, our potential difference is that voltage between the two ends. Are we together there? Therefore, look at what we listed down. Let us see some of the limitations of Ohm's law. Remember, as you see here in the statement of the law, it is restrictive. They are saying that provided the temperature and the other physical conditions are kept constant. That means that some of the limitations of Ohm's law, so it is only applied when temperature is constant, temperature and other physical conditions. That's why it is restrictive. That means if temperature is not constant, the law does not apply. It's only applied when temperature is constant. That's one limitation. Then another limitation, you can say that it only applies to metals. It only applies to to metals. It does not apply to certain materials. It only applies to metals. That's why they have said passing through a conductor. Remember, all pure metals are conductors. What if they are semiconductors? That means to semiconductors, the law does not apply. It must apply to conductors. So the limitation I can give you there, it only applies to metals, but not non-metals, and it is only applicable when the temperature and other physical conditions are constant. And then we have what we call the ohmic conductors and the non-ohmic conductors. Like you see the word ohmic. Are we together there? Ohmic conductors. This means that these are conductors which obey Ohm's law. That's why we call them ohmic conductors. For example, metals, and some of the pure metals we have like iron, we have zinc, we have copper. Those ones obey Ohm's law. It's a simple definition. Ohmic conductors are conductors which obey which obey Ohm's law. And then we have the non-ohmic. The non-ohmic conductors. Non-ohmic conductors, that's just the opposite. It's contrary. So you say non-ohmic conductors are conductors which do not obey Ohm's law. These are conductors which do not obey Ohm's law. Like non-metals, semiconductors, for them they don't obey. Then we are going to see the graphs of current against voltage for the ohmic and the non-ohmic conductors. Some of the graphs for ohmic conductors, graphs of current versus voltage. For ohmic conductors, remember, voltage here in volts, then we have current in amperes. In this case, for all conductors which obey Ohm's law, the ohmic conductors, we see current is directly proportional to the what? To the voltage. That's why you are seeing a straight line through the origin. That is their graph. All conductors which obey Ohm's law, it is the same. It has to have this linear relationship. Then for non-ohmic conductors, you know, non-ohmic conductors, it depends which non-ohmic conductor are you talking about. You can be talking about like electrolysis of sulfuric acid. You can talk about like electrolysis of sulfuric acid. In this case, the graph will look like this. Are you seeing it? If we have current here in amperes and we have voltage here. Those are the graphs of current versus voltage. So that's how it will look like electrolysis of sulfuric acid. Then we can have another one. Remember, all those ones are non-metals. We can have like for inert gases. Inert what? Gases. Like for example, I can give an example like maybe neon gas. It's a good example there. It will look like this. Very simple. This is your current against maybe this is voltage. Now on the inert gases, a good example I've given that neon gas. That's how the graph should look like. You see the shape, and be careful about naming the axes. This, don't call it Y and X. So just this is the for current in amperes. These brackets, you have to be careful, and that's the voltage in volts. Then filament lamp, that's the shape. We consider the shape so much. Then semiconductor diode, like you see that shape. Vacuum diode, hope you have seen it. Current versus voltage. And lastly, the thermistor. But what you have to be careful about, the vertical axis, I say current versus voltage. The SI units, don't forget them in the brackets. So those are your graphs. And then lastly, we are going to end here for today. We shall continue with what next in our next lesson. We see the circuit symbols, and then we switch to the Ohm's law verification. We do the experiment. Thank you very much.